If you are a video gamer and have played those RPG games like Diablo, you probably have spent hours farming a good weapon because some attributes of the weapon are actually RNG, which means they are generated by random numbers. Or maybe in other games, you can imbue your weapon with extra attributes by using certain resources. Some of them might be real money, and still, those attributes might be random values distributed in a prescribed interval. Every time you click the button, your resource is consumed, and random attributes are generated. And of course, everyone wants to get the best one with minimal resources wasted. If you are very unlucky, you might not get your ideal weapon even after you already dump a lot of resources into it, and you are confused when to stop. Think about it. If now this weapon on the screen does not give you the ideal attributes you want, would you click the Reforge button in the hope of getting a much better one? Okay, if you do it, you probably get something even worse, or maybe something you really like. What I want to say is that even though it's very random, there is actually a concrete strategy you can follow to maximize your profit, as long as you know how much you value the resources you spend and the attributes you get back. Let's play a very simple game here. Here's a button you can click, and if you click it, it costs you a coin. Well, sounds like a very stupid game because why would you waste a coin? So let's make it more fun. Once you spend a coin, a random number is generated among 1 and 100 equally likely, and whatever number you get as a result, that number of coins will be rewarded back to you, and you may click the end game button to take them away. I guess now you start to like this game because this is a game you can never lose, right? If you are unlucky and not satisfied with the current result, you may choose not to end this game and spend another coin to reroll the result. Maybe you get a 100 next time, who knows? But keep in mind that every time you choose to reroll, you spend a coin, and the rerolled result will overwrite your previous ones, and you can only play this game for one time. Now the problem is, what strategy should you employ to maximize your profit? Well, the word maximize here is a little bit weird, because it's not in our control which number we get, right? It's all random. Yes, that's true, but a person who is so stubborn to get a 100 is very likely to earn less than someone who is satisfied with, say, 90. Because getting a 90 might take you only a few coins, but getting a 100 may take you even more than 100 coins if you are really unlucky. So what we are really asking to maximize is not the profit, but what the mathematicians call expectation of the profit. If you don't know what it is, it's fine. Let me illustrate with a very simple example. Rolling dice is random, and you get one of the 6 results when rolling a 6-faced dice, and they appear equally likely if the dice is fair. But if you roll the dice multiple times and take the average, you are actually expected to get a 3.5, which is the average from 1 to 6. So the expectation is not something you must get in a random event, but something you should expect if this random event happens a lot of times and you average them out. Now we have clarified the problem using more rigorous mathematical language. How should we proceed? You may pause the video and try it yourself for a few minutes. A very nice starting point is to consider what happens in the 50th round. So you are really unlucky, and you already spent 49 coins and not even hitting a single number you are satisfied with. Now my question is, no matter what strategy and what results you obtain in previous rounds, what should be the goal of this round that you should be satisfied with? Again, pause the video and think about it. The answer is very simple. You should be satisfied with whatever result you get, even if it's just 1. Why? Let's assume you are not satisfied with the number you get, no matter what it is, and proceed to spend another coin to play another round. Now you have spent already 51 coins, but how much do you expect to win? The answer is simple. It's like rolling a dice of 100 faces, and the expectation is just the average, which is only 50.5. So your expected net profit is actually minus 0.5 if that happens. Again, let me emphasize we're discussing things from statistical point of view. You may actually get a 100 in your 51st reroll and walk away with 49 coins, but that's not very likely and statistically not favorable. Therefore, the conclusion is, you should end the game no matter what result you get in your 50th round, and you are expected to end the game and go home with a half coin. which is obtained by 50.5, the average from 1 to 100, minus the 50 coins you have to pay. Now we figure out the 50th round. What about the 49th round? What if you are not satisfied with your previous 48 rounds and decide to reroll again? What should be the number you are satisfied with? In order to answer that, let's call the goal number n, which is something mathematicians always do. They use a symbol to indicate something, and figure out later what that symbol actually is. Now there is a dissection of the scenario. You end the game if the number you get this time is at least the number n. Otherwise, you spend another coin to reroll. The n is determined in the following way, that your profit of ending the game at this round should be greater than the expected profit of playing another round. Well, I know it sounds horrible, but let me explain. Recall that if you play the 50th round, you should be satisfied with whatever result you get and walk away with an expectation of owning a half coin, right? So that means you should end the game if you get at least a 50 in this round, because subtracting the 49 coins you pay, you still walk away with 1 coin, which is more than you are expected to gain if you play your 50th round. So n should be 50 at round 49. You end the game if the result is at least 50, otherwise you reroll. Now, let's calculate how much you are expected to win at round 49. If you employ the strategy of rerolling below 50, here's the result. Again, looks intimidating, but actually very easy to understand. This is the probability that you roll less than 50 in this round, which is 49 over 100, and the 0.5 is the expected net profit in that scenario. You have a 1 in 100 chance to roll 50, which gives you 50 minus 49 equals 1 coin. You have another 1 in 100 chance to reroll 51, which gives you 2 coins in reward. You continue this pattern until you have 1 in 100 chance to roll 100, which gives you 51 coins in that case. If you calculate this, you are actually expected to get about 30.5 coins in your 49th round of play. Now you know how much you are expected to win in round 49. You go back and consider round 48. It is analyzed in exactly the same way. You are expected to win 30.5 coins if you play round 49. That's something we just calculated. So in round 48, you should be satisfied with 62, which is obtained by 48, which is the coins you have to pay, added by 30.5, which is your expected profit if you play another round, and you round it up to the next integer, which is 62. Similarly, you can calculate the expected profit if you set the goal to be 62, and that's evaluated to be about 21.1, and so on and so forth. You keep tracing back to the target and the expected profit of previous rounds. If you do the whole calculation, the strategy to maximize your expected profit is given by the following diagram, where the horizontal axis indicates which round you are currently at, and the yellow and blue points show respectively your target and expected profit in that round. You may notice that the yellow dots are very stable near 87 for the first 40 rounds, after which it starts to drop very fast. And if you think about it, 87 is not a high goal and it's very likely reachable if you try 40 times. So if you don't want to do all the Nancy calculation in this video, the takeaway is just wait for 87. And in fact, there is a much faster but conceptually harder to understand way to show that 87 should actually be your goal. Let's set n to be the target and let en be the expected profit with this strategy. You end the game when you get a result at least n, and the expected profit for this part is given by the expression below. This expression literally means if you roll n, you go away with n minus 1 coins. If you roll n plus 1, you go away with n coins, and if you roll 100, you go away with 99 coins. All of them happen equally likely with probability 1 in 100. Also, you choose to reroll if the result is less than n, which happens with a probability n minus 1 over 100, and in that case, your expected profit is en minus 1 because you have to pay another 1 coin to reroll. Combine these two expressions, we get the following. We may solve out en as a function of n, and the maximum of this function occurs at n equals 86.85, which is approximately 87, and the expected profit is about 86.35. This method is, rigorously speaking, not correct, because it is treating the target n as a fixed goal, not depending on the current round, and it assumes you reach the goal within the first 1 or 2 rounds. Both assumptions are not true. However, it is still very accurate, especially in the first several rounds, because the cost it takes to reroll, which is only 1 coin, is not really much in a scenario if you roll a very terrible number. And that's why in this graph, you see a very stable value of the target for the first 40 rounds, but the expected profit diminishes constantly because every time you reroll, you lose a coin. Besides, though we are using the expected profit as a metric of how good the strategy is, but in many scenarios, it's not the case. For example, in the famous St. Petersburg game, you pay an entrance fee to play a game. The initial stake is $2, then a fair coin is tossed, and every time it is a tail, the stake is doubled, and the first time a head appears, you take the money away. If you calculate the expectation value, it turns out to be infinity. So you are expected to win an infinite amount of wealth by playing this game, and the casino may charge you $10 billion for a single play and still can claim you that you are taking the advantage. However, how much do you really want to pay this game? Maybe not even $100, because you have a 50-50 chance to lose in the very first round and walk away with only $2. That's also why mathematicians introduce terms like utility functions and others when they analyze a scenario like this. Anyway, that's beyond the scope of discussion of this video. I hope you enjoyed this video and get the best weapon in your favorite game, and even if you don't, you know when it's the best time for you to stop. Like and subscribe if you enjoy solving interesting math problems in your life. See you next time.